Hello everyone. My name is Charles Chan. I'm currently working at Intel as a cloud software development engineer, and I will be the moderator of this session. So the topic of this talk is accelerating 5G mobile core control plan using P4. And it's my pleasure to introduce our speakers, Jingqi Huang and Jiayi Meng. Both Jingqi and Jiayi are pursuing their PhD degree at Purdue University. In today's presentation, they will highlight various characteristics of the 5G core control plan, explain why it is becoming a hotspot and why state-of-the-art solutions fell short in meeting its performance and scalability requirements, and discuss how P4 programmable NICs and switches can help accelerate various stages of the 5G control plan. So Jingqi and Jiayi, please take it away.
Okay. Hi, everyone. My name is Jingqi Huang from Purdue University.
Hello, everyone. This is Jiayi Meng from Purdue University. Today, Jingqi and I would like to present our recent work, accelerating 5G mobile core control plane using P4. And this is a joint work with our advisors, Charlie and Shabazz from Purdue University, and also Iftaka and Christian from Intel Labs. In this talk, we will first share with you the insights of our experimental results in today's 5G core architecture, and then discuss how we can accelerate it using P4. Nowadays, as there are increasingly emerging applications envisioned in next-generation mobile networking, we are now at a turning point where humans are no longer the only primary consumer of data. Not only there are more cutting-edge applications for human-to-data interactions, such as augmented reality and virtual reality, but also there are going to be more and more applications designed for the device-to-data interactions, such as massive Internet of Things, self-driving cars, etc. Those emerging applications set new requirements for mobile core in order to achieve high quality of service. First, the mobile core should be high performant. This means that the core should provide not only high throughput, but also low latency. Second, the core should be scalable to support large-scale users. Here, by large scale, we mean billions of users and devices accessing network services at the same time. Third, the core should be flexible, which means it's easy to manage and upgrade in order to support more applications with new requirements. However, today's mobile core that is LTE is vertically integrated. It means that it's not easy to scale for a larger amount of users or to upgrade for any new requirements. Why is that? If we look at the mobile network architecture of LTE, specifically, let's zoom into the middle part, where there are 5 components surrounded by the red dash box, which are mobile core network functions of LTE. And all of them are designed and embedded in dedicated hardware, which results in poor scalability and flexibility. To make the mobile core scalable and flexible, 5G mobile core is re-architected into a horizontally disaggregated mobile core. Unlike LTE, network functions in 5G core are designed as microservices and expected to be run on commodity servers. Moreover, 5G core separates the network functions with database, so that the major network functions in 5G core are stateless. This architecture is called service-based architecture. With such architecture, 5G core can now be scaled to support more users by simply adding more network function instances. And it can also be easily upgraded, since network functions are just softwares running on the server, instead of being embedded in the hardware. Next, let me quickly highlight the 3 most important network functions of 5G mobile core to give you a better picture of it. The first one is AMF. It is the key component to connect UE, G-Node B to the mobile core control plane. It is responsible for connection and reachability management, mobility management, etc. And the second one is SMF. It manages each user equipment session, including IP address allocation, selection of associated user plane function, etc. And the third one is UPF. It is basically the data plane of 5G mobile core. It is mainly responsible for forwarding data traffic between GNode B and the internet. Now you may wonder, how do those microservices exactly interact with each other to provide network services to the users? Next, let's quickly go through the life cycle of the most dominant control event in cellular networks. That is service request. Service request is triggered for the UE and GNode B to build a connection with AMF and activate an associated user plane connection so that the UE can send or receive data and control traffic. To achieve it, first, UE sends a service request to GNode B. Next, GNode B encapsulates the service request with some N2 parameters as an N2 message, and then forwards it to AMF. After receiving N2 message, AMF sends an update SM context request to SMF. And then SMF will select the UPF for the UE. After selecting UPF, SMF sends an update SM context response back to AMF. Then AMF sends an N2 request with information required by GNode B to set up a secure connection with the AMF for the UE. And the GNode B and UE finish the setup. Then GNode B sends another N2 request acknowledge the message to AMF. Then AMF sends another update SM context request to SMF. SMF sends session modification request to UPF, and UPF replies session modification response to SMF. SMF then sends an update SM context response back to AMF. And this is the workflow for service request, which involves several transactions between network functions. And among all the network functions, AMF and SMF are the primary components involved. So far, we have talked about emerging applications set new requirements to mobile core, which drives the mobile core to be re-architected. Next, let me share with you another important observation. That is, 5G control plane traffic should be increasing compared to 4G. It mainly increases in 3 dimensions. The first one is increasing UE number. Based on the forecast of Ericsson, 5G subscription is expected to be reaching 4.4 billion and become the dominant mobile access technology by 2027. And the second one is increasing control event frequency. The most well-known one is handover. As handover happens when the UE moves and changes the serving base station, there are expected to be more handovers in 5G than in 4G because of 5G's smaller base station coverage. The third one is increasing transaction number per event. This is resulted from the mobile core re-architecture from 4G to 5G. Now, Jingqi will take over and introduce our characterization study of 5G core.
Okay, to characterize 5G core control plane, we have set up SD core, which is from ONF Ether project. It is powered by Kubernetes. And each network function in the blue box is running as microservice in a Kubernetes port. It is initially based and forked from an open source project 5G-C in 2020. It supports 5G standalone mode, which does not overlay on an existing 4G mobile core. SD core currently supports major 5G control events, such as service requests, PDU session establishment, register and deregister, handover, and others. After setting up the 5G core, we also build a traffic generator. With a traffic generator, we can simulate different number of GNode Bs, and each simulated GNode B is a process running in a Kubernetes port. Within each GNode B, we can emulate different numbers of UEs, and each UE is a thread in the GNode B port that can trigger control event. In this way, the traffic generator can let different numbers of UEs triggers different control events. After setting up the Ether core and the traffic generator, We did some primary experiments to characterize the 5G core to find out its hotspot or bottleneck. More specifically, we assign different numbers of CPU cores to 5G core control plane. We also initiate different numbers of UEs in the traffic generator. And all UEs are connected to the control plane network function simultaneously. We then let each UE trigger service request in a back-to-back way. Meanwhile, we are collecting statistics that we are interested in during the experiment, such as latency and CPU usage. Let's first look at the end-to-end latency of service requests. ETSI standard recommends the control plane latency to be 10 to 20 milliseconds. Here we can see that when UE number is larger than 20, the average end-to-end latency exceeds the 20 millisecond requirement, even when we assign 48 cores to the 5G core control plane. This indicates that current system scales poorly with increasing UEs. Recall that previous service request example and references pointed out that AMF and SMF are the two major network functions in the 5G core. This is indicated in the CPU usage. We plot out the CPU usage percentage of AMF and SMF over all the 5G control plane network function. We can see that in all the experiments, AMF and SMF together take up over 90% of CPU usage of the 5G core control plane. So from the CPU usage point of view, AMF and SMF are indeed two major network functions that may have room for acceleration. We then look into the processing latency of different transactions of service requests. By processing latency, we mean the duration between finishing one transaction and starting the next one, as shown in the left figure. Because the ranking of all the experiments are similar, let's take 24-core 100 UE experiment as an example. From this processing latency breakdown, we can see three outstanding transactions: N2 message with service request, update SM context request and response. Note that the processing of N2 message with service request will not be finished before the last service request is fully completed in the 5G core. And in our experiment, we are actually sending service requests once GNOB got feedback from AMF, which is after the initial context setup request. So the high processing latency of this N2 message most likely happen when a UE is sending multiple service requests in sequence. But the other two transactions with high processing latency, update SM context request and response, are the transactions we are interested in, since they are only affected by the AMF and SMF. These two transactions are at least 6 times higher than the processing latency of other transactions. Some people may think that assigning more CPU cores to the 5G core control plane may help with accelerating it. This is correct in some cases, since we saw latency improvement in the previous slide. However, we also observed that in our 300 UE experiment, scheduler uses more CPU as the core number increases. When we increase the CPU core number from 6 to 48, we clearly see that the CPU usage increased from 5% to nearly 50%. More importantly, this increase is not linear. The impact of the scheduler will become much worse as more core assigned. So to sum up the insight from the characterization, we know that current system scales poorly with with increasing UEs. AMF and SMF are hotspots in CPU usage. And when we zoom in to the transaction level, processing latency of N2 message with service request, update SM context request and response are the bottleneck transactions. And we also discussed the impact of the scheduler when CPU core number increase. Scheduler uses more CPU when the core number is increasing. Recall that there is an ongoing wave of disaggregating 5G core control plane into microservices. And we want to accelerate these services using P4 programmable data plane, such as SmartNICs. But traditional P4 merge action table are too restricted, since they can only do simple single cycle actions. So we need something more flexible and stable to offload 5G core network functions. Therefore, we are proposing a P4 programmable hardware design for 5G core control plane. We extend the traditional P4 match action table to match lambda abstraction and offload the bottleneck functionality to the P4 programmable hardware. Here we show SMONIC as an example. This is to leverage the high performance feature of the programmable hardware. Match Lambda is a new programmable framework exposing an event-based programming abstraction. Next, I will introduce the three major design components of Match Lambda abstract. The first design component is abstract machine model. Mobile operators will write their Match Lambda function against an abstract machine model as shown in the figure. In this model, lambdas are independent programs that do not share states. Only a matching loop can invoke these functions. Also, the matching state serves as a scheduler that forwards packet to the matching lambdas. Finally, a parser handles packet header operations, and lambdas operate directly on the passed header. This property of the machine model will make it easier for mobile operator to express functions by separating out the passing and matching logic. The second design component is programming lambdas. Mobile operators will provide one or more lambdas for their network functions like send, update, SM context requests. The function can be written in micro C or other feature-rich language like Python. The figure shows that the signature of the top level function having two arguments, headers and match data. The match data T is the extracted header T data structure specify the number and the structure of all the supporting headers. And the match data T specify the function parameters. These two will both be predefined. The lambdas will operate directly on these parameters and headers without having passed the packet, which is done at the passing stage. The last design component is expressing the match. The user can further specify the corresponding P4 code for match stage as shown in the example code. During a comparison, a workload manager will assign unique ID to these lambdas and share this mapping with the gateway and populate the ID variables. For example, the HTTP registered UE context process ID in this example code. For each incoming request, the gateway will insert the ID of the destined lambda as a new header. The match stage as defined in the P4 code will check the ID listed in the new header and will call the matching lambda. In the end, the workload manager will pair the lambdas and match stage in a single match lambda program and prepend it in a cellular specific P4 packet passing logic. It will then compile and transfer this program into a format that programmable hardware can execute. Summing up this presentation, we first show that 5G core is hosting more emerging application and control plane traffic. To meet the scalability and flexibility requirement, 5G core is re-architecting. It is disaggregating into microservices. By conducting different experiments with major control plane events, service requests using Ether SD core, we find out that current system scales poorly with increasing UEs. We also show the bottleneck function and operations. Finally, we propose a P4 programmable hardware design for 5G core control plane. Especially, we also propose match lambda abstraction to ease the development. Thank you for listening, and we are happy to take any questions.
All right, thank you guys for the very great presentation. I have 3 questions for you. The first one is that in the architecture diagram you show in the proposed solution, that only part of the core functionalities are offloaded to the P4 SmartNIC. Can you give an example on what type of workload can or should be offloaded and what should remain in the containers?
Yeah, that's a really good question. So the offloaded functionality should be the functionality that is bottlenecked the transactions, such as update SM context we mentioned in our presentation, and like the functionality that needs stateful, that needs a lot of stateful operation. I think they should maintain in the container, since we all know that the program hardware is not that good on doing stateful operation than the containers.
I see. All right. I think that also come to my second question. You gave an example of using P4 to offload the update of the session management context, right? And there can be a lot of sessions in IoT use cases, since the offloading is based on this match lambda table you're proposing. I guess the number of sessions that can be supported will be mainly constrained by the hardware resource. Is that right?
Yes, you are correct. So of course, the number of sessions that we can support is related to the processor in the number of processor in the such as SmartNICs. I would say that I am envisioning that our design would embed many micro core like RISC like cores in the SmartNICs. In this way, we can do a lot of parallelization job and support more PDU sessions, for example.
Have you evaluated roughly how many sessions or UEs you can support using a off-the-shelf SmartNIC platform? Or like, maybe have you done like simulations of scales?
We haven't done it yet, but we did some survey, and the SmartNIC can support, I think, hundreds of such small cores. So ideally, it should be one core should support one session operation at a time. So ideally, if this structure holds, then our design. This kind of design can support hundreds of sessions simultaneously.
All right, sounds good. And my last question, you show a few interesting diagrams at the beginning about the latencies and CPU consumptions of the traditional approach using containers. But I don't see such data for the P4 offloaded approach. It would be really interesting to see the comparison between the CPU-based solution and SmartNIC accelerated solution. Can you give a rough idea that how good we can get in terms of latency at large scale if we offloaded that to the SmartNIC?
We haven't did experiment or simulation in P4-based platform, so I cannot get very detailed message. But I think by the previous work that the operation in SmartNIC is line range, they can be as low as nanoseconds. So we are expecting at least it should be below the ETSI standard recommendation, the best recommendation, which is 10 milliseconds, and we are hoping it to be sub-millisecond.
All right, sounds good. Thank you, Ving, for the presentation. That's all the question I have.